Welcome. In this video, we're going to be going over the 4 types of feedback that you'll see. And it basically depends upon how the input is applied and how the feedback signal is mixed with the input and how the output is sampled. So let's get started. So as I mentioned, we're going to be going over what I call the 4 feedback approach. So this is a method to analyze feedback circuits. Now, it's commonly taught in engineering schools, but what you'll find is it's almost never used in industry. And we'll just talk a little later about why that's the case. So then you might ask, well, then why cover it at all? Because it's still a very useful technique to get an intuitive understanding of how feedback circuits are created. It's just not that useful for analysis. So it gives you some idea on how feedback circuits are created, how you sample the output, how it's mixed together with the input. But when it comes down to analysis, it generally is not that useful an approach. And again, we'll discuss that after we look at the actual categorization of these 4 feedback types. So it's useful for categorizing your feedback type, but as I mentioned, it's not really that useful for analysis. So what we do is we'll say that there are 4 basic feedback structures. Because if you recall, we said the input can either be voltage or current, and the output can also be either voltage or current. So what we find is we have our normal feedback structure shown here. We have our inputs and the feedback signal, so they all have to be the same type. We have our output. When I say type, they have to either all be voltage or all be current. Then we have our output shown over here, X sub naught, and that's either voltage or current. So then we can break this up into 4 different types here. We can say that there's 4 types, depending upon whether we use voltage or current for the input, and depending on whether we use voltage or current for the output. So what we have is we have our 4 types, where the input is shown over here, so the X sub S, the feedback signal, and X sub I all are the same type, and the output is shown here. So we either have the input being voltage and the output being voltage. If we have that, we call it a series shunt feedback circuit. And that's the type of feedback circuit, and the series refers to the series right here refers to the input type, and the shunt here refers to the output for this feedback circuit. So the other possibilities is we can have the input being current, the output being voltage, in which case we'll call that a shunt configuration. We can have the input being current, the output being current, and we'll call that a shunt series configuration. And finally, we can have the input being voltage, the output being current, and we'll refer to that as a series configuration. So the series shunt here would mean that the output is a voltage, and it's sampled with a shunt network. Well, the input is also a voltage in this case, and the subtraction is done with a series network. So then your question may be, well, why are we using this terminology? Why are we using the terminology series and shunt? The reason for that is that if we look at the input summation, we'll see that when we want to sum the input. So what we have in our original feedback circuit, we have a summation right here. So we need to take the input signal, the feedback signal, and sum them together. In fact, the input signal minus the feedback signal, and that creates the error signal here. So we need to have a summation. But if we're summating things, so if they're voltages, then we add them by putting them in series. In other words, if I have a V sub S and I have a V sub F, so a voltage which is here, a voltage here, which is V sub S, another voltage which is V sub F. If you notice, I've actually made the positive and negative reversed here, so that when we subtract these, or when we put them in series, so when these two are put in series the way they're shown here, then if I look at the voltage from here to here, we see that voltage is V sub I, which is the source voltage minus the feedback voltage, because we have a minus V sub F here and a positive V sub S here. If I sum those two together, it's Vs minus V sub F. So I place voltages in series in order to subtract them. Now if my signals happen to be current, so if my input was a current and I needed to subtract that from the feedback signal, then to add or subtract them, I put them in parallel, which is also known as a shunt. So in other words, if I have, in this case, I sub S is a current going in this direction, I sub F is a feedback current going in this direction, then this current, I sub I, the error current, would be equal to I sub S minus I sub F. So I place, in this case, the two currents in parallel or in shunt. And now you can see why we have the terminology series and shunt. Now in terms of sampling, this was looking at the input mixing, how we mix our feedback together with the input. But we also need to look at how we can sample our output, because we want to use that, go into the beta network. In other words, if we look at the original circuit here, we need to somehow sample X sub naught. We need to sample X sub naught here and then pull this into our beta circuit. So now if the output is a voltage output, then we sample it just by taking a parallel or shunt connection. So in other words, in this case here, if our output happens to be a voltage, V out, we can just make a parallel connection here and feed that into our beta network. Now if the output happens to be a current, so if we say we have our current output over here, I sub out, and we want to sample that into our beta network, then we need to put that in series the way it's shown here. So we have this current I sub out flowing through here, going into our beta network and coming in this way. So we know that we'll always have this current equal to this current, and we'll also have this current going into the beta network equal to the current coming out of the beta network here. So we need to sample our current, we need a series connection as opposed to a parallel shunt connection. So then we can write or draw our four different types of feedback. We have a series shunt. So in this case here, we would have our shunt at our output. So we can see we have a shunt connection for the output. But in order to have the voltages sum together, we have a series connection here for the voltages. So if we look at the voltage here and call that V sub F, the feedback voltage, and we call this here the error voltage, we can see that this error voltage will be equal to V sub I will equal V sub, call this voltage here V sub S1, because it may not be exactly the same as V sub S over here, because we do have a resistor, source resistance over here. So V sub I will be V sub S1 minus V sub F. We also look at a shunt. So the output system over here is exactly the same as the output system over here, because the output is shunt in both cases. But now for the feedback portion, mixing, we have mixing as a shunt. So they're in parallel over here. And again, we have that in this case here, if this is the I sub I going into that and coming out of this amplifier circuit. And we have our feedback currents over here. And this is I sub S1. Then we have that I sub I is equal to I sub S1 minus I sub F. And so we subtract them off by using a parallel combination. Notice we can always do a current source equivalent for this voltage. So this is just a Thevenin. We're showing it as a Thevenin resistance or a voltage source equivalent. But you can always do a current source equivalence by just making it into a current source in parallel with the resistor. So we've always drawn it the same, but this, of course, you can draw this part over here. You can always draw that as a current source in parallel with R sub S. And this would be V sub S over R sub S. And then this would be exactly the same as the voltage source equivalent. And I sub S then would be equal to I sub S would be equal to Vs over Rs. So this would be equal to I sub S. And I sub S1 might be a little bit different because now you do have a parallel R sub S here. So finally we have the last two types. We have the shunt series, where this part is the same as here, but we now take the output and we put this in series because we're sampling the output current. So in this case over here, we've changed the output stage here because we're now sampling the current I sub out going into the feedback network. In order to sample that current, we need to have a series connection. And so finally we can do a series over here. And the series is, as we've already seen it, at the input, and the series is the same as we just saw up above for the output. So we have the four different types of our feedback networks. Now, that's fine in a block diagram, but what does it actually look like in a circuit? So let's do some examples. So here's some series shunt. So it's probably one of the most common ones that you might think about because it's a non-inverting amplifier for an op-amp. So it's fairly straightforward. Let's look at this example. So we have our input over here. It's applied to a non-inverting amplifier for an op-amp. And we can see in this case, we're sampling the output. So V out, So V out here is being sampled with a parallel connection going into our beta network. The beta network is this network here. This creates an output voltage V sub F. That's in series using this differential amplifier with V sub S over here. And we create the error voltage V sub I right here, and V sub I will be equal to V sub S minus the feedback voltage. Now, it's always useful to check that we have negative feedback around our loop to make sure that we haven't, for some reason, have positive feedback. If we switched these two connections over here, we'd have positive feedback rather than negative feedback, and then our system would not be stable. So we would like to check that it's actually negative feedback. And one way we can do that is we can just assume, just for the sake of finding whether it's negative feedback or not, that things change very slowly around our feedback loop. So what we can say is that if things change very slowly, and we could say that when VS1 increases, so I'll write that as this terminology here, VS1 goes up, then what we see is that if the feedback loop, so going around this loop over here, does act very slowly, then V sub F will not change. So if I assume it doesn't change instantaneously, it just takes some time to change, what we know is that when V sub s goes up, V sub I will also go up. So it will also increase. So when we increase V sub s1 here, if this stays constant, then V sub I increases. And that's what this this terminology here means. So the terminology V sub s1 increases results in a V sub I increasing. So it means V sub I increases results in V increasing. And as I said, that assumes that the feedback loop, going around that feedback loop, is very slow. So now if we look at our circuit that we have here up above, we have that V sub s1 increasing results in V sub I increasing. If V sub I increases, that will result in V out increasing. That's because we have a V sub I is on the positive and minus terminal of A, so V out is equal to A times V sub I. So we have the V sub out is just A times V sub I, so if Vi increases, then V out will increase. A is positive. And then if V sub out increases, so if this value here goes up, then V sub f will also increase. If V sub f increases, that decreases V sub I. So what we see is we've gone around our loop here, and we've resulted in that V sub I increased, resulted in V sub I decreasing. And that means that we have negative feedback around our loop. So since V sub I is increasing, results in V sub I decreasing, we know we have negative feedback. If we found that V sub I increasing resulted in V sub I also increasing, going around the loop, then we'd have positive feedback. And as I mentioned, that would generally not be a good thing unless we're building an oscillator. And we would want to avoid that. So we'd have a stable system as opposed to an unstable system. Now that was an op-amp example of a series shunt feedback circuit. Shown here is a circuit example of a series shunt feedback circuit. So in this case here we have again our input being applied over here, creating V sub s1, we have our error voltage V sub I here, and we have our feedback signal V sub f here. So our beta network, once again, is this two resistors that we have here. And we're sampling the output because it's a series shunt. We're sampling it as a shunt connection onto the output. If we look for the stability situation here, see whether it's negative feedback, we say that V sub s1 increasing causes V sub I to increase, as before. In this case here, if V sub I increases, V sub 1 will decrease. So that results in a V sub 1 going down because it's inverting from V sub I to V1. Then if V sub 1 goes down, that will result in V sub out going up. So this will go up because there's an inversion over here. So now we have the V sub out, V sub naught going up. If V sub naught goes up, that will, because this is now a non-inverting to V sub f, we have that V sub f will also go up. Now the final part though is that we have now, we're at V sub f going up, so we have V sub f going up here, but the gain from V sub f to V sub I, we'll see that that is actually going down. Because V sub I f goes up, that's going to reduce V sub I, and we have that the input voltage will go down. And so we do have negative feedback around here because we, as before, we have the V sub I going up, results in the V sub I going down, so there's negative feedback. Now, at first glance, you look at this and you think, well, why is there negative feedback? Because we have inverting gain from here to here, then another inverting gain from V1 to V out. Well, that's true from the input perspective. from the feedback's perspective, we have inverting gain from V1 to Vout, but from VF back to V1, it's actually non-inverting because it's a common gate amplifier. So we only have one inversion around this loop, and so it is in negative feedback. So that's another way of sort of checking for negative feedback, is ignoring the input altogether and just going once around the loop. So the next example we have is a shunt example from a circuit perspective. So in this case here, we have, as usual, we have our input signal over here. But because this is a shunt connection that we have for our feedback, we actually will be more interested in the current I sub s coming in. What we have is the feedback signal is shown over here. The error current is shown here. So the error current is equal to this signal current minus the feedback current. And once again, looking for negative feedback, we have that if we increase the current I sub s, if I sub f remains unchanged, then the input current, or the error current I sub I, will increase. An increase in this current here will cause this to go up, which will cause Vout to go down. So we'll have Vout will go down. Vout going down will make I sub f increase. So I sub f will increase. If I sub f increases, that will decrease the error current, which we can see from this equation here. So as before, we have that an increase in the error current results in a decrease in the error current. So we have negative feedback, and that's good. It's a transistor level circuit that is now also shunt. So we can see that shunt over here, and we're sampling the output over here, which is also shunt. If we go around this circuit, we look for the feedback, we'll see that V sub s going up creates I sub s going up, so this goes up. The error current increases, which will make V1 decrease because it's inverting from this voltage to this voltage, and I sub I increasing will increase the voltage there. So we have that V sub 1 will go down, V sub 1 goes down, will cause V sub out to go up because it's inverting from V1 to this stage. So V sub out will increase. V sub out increasing will cause the feedback current to decrease. So if this voltage here goes up, then that decreases this. In other words, if you imagine that we had 0 volts across here, if I bring this up, current will actually flow this direction, which will be decreasing I sub f. So V sub out increasing reduces I sub f, and reducing I sub f will actually increase the input current. So that is what we don't want to see. So if we look at this, we have that an increase in the error current results in a further increase in the error current. So this is actually positive feedback. And now how do we see that? We can see that, again, if we ignore our input altogether, we have an inversion from V1 to Vout, and then that would also result in this voltage here, and which is non-inverting, but another inversion from here to here. So we have 2 inversions around this loop, from V1 to Vout and from Vout back to V1, which would be 2 negatives, which makes it positive, so we have positive feedback. How can we change that circuit? We could get rid of this other inverter. So this inverter here, non-inverter, sorry, this other negative amplifier. We can eliminate that one and just have a single transistor. And this would be an example then of a shunt circuit. And you can go through this one, and we'll see that I sub I increasing will result in I sub I decreasing because we don't have this extra inversion around the loop. Next example we want to cover is a shunt series example. So we want to look at something where the output now becomes a series sampling. So in this case here, the shunt part of it is the same as we've seen. So the input side over here is very similar to what we've seen. We've just redrawn this as the current source equivalent rather than the voltage source equivalent here. So what's different though is that we're actually now looking at the output current up here, which is I sub naught, and that's going into our beta circuit. So our beta circuit now, or our feedback circuit, is this over here, and it's a current coming into it. So we have I naught coming into this, and that creates a voltage V2, which then will also create a current I sub F over here. So if we look at this case, again, we can look for negative feedback. I sub S increases, which will increase this current, which will increase the error current. That will decrease V sub 1, which will then, because this is a non-inverting from V sub 1 to V sub 2, so V sub 2 will also decrease. A decrease in V sub 2 will increase I sub F, which will decrease I sub I. So we have negative feedback, as we would hope to have, and it would be stable. Finally, a series example is shown here. In this case here, we're taking, again, similar to what we had before. So we have a output current that is sampled over here as also the output current. And that will then go around and mix with a series input. So if you notice our mixing is now done in this part right here. So our feedback network in this case is going to be these resistors over here. And we have looking for negative feedback, that if V sub S increases, V sub I will also increase, which will make V sub 2 here go down because it's inverting, which will also go over here. V sub 3 will also go up now because it's also inverting from V2 to V3. V sub 4 will stay increasing because V sub 3 to V sub 4 is non-inverting. That will result in V sub F going back over here to also be increasing. If that increases, V sub I will decrease. And so we have, as before, that an increase in V sub I results in a decrease in V sub I, so we have negative feedback around this loop. Notice for this example, there's no biasing shown. We just have these resistors connected to ground. So this is really a small signal representation of our transistor circuit. This would normally have to be going to a power supplies over here, or there'd be current sources and other ways to do this. But we really are just showing the small signal representation for this circuit. So now, I want to go back and discuss this 4 feedback circuit approach. So as I'm going to refer to this as the 4 feedback approach. And as I mentioned, it's almost never used in industry. And there's 3 main reasons why it's not used. You can see it was useful for sort of looking at a circuit and seeing how the signals are mixed at the input and how they're sampled at the output. So it might help you to create a circuit. But for analyzing, it turns out it's not almost never used in industry. And there's 3 main reasons for that. So the first, it turns out it's fairly difficult to use. I've seen many professors mess this up. What you find is that the same circuit, but with a differently defined output, will change the type. So you take the output in a different location, and all of a sudden it becomes a different type of feedback circuit. And that ends up being prone to errors. So where you apply your input and where you take your output affects the which of these 4 types you decided to be, and I've certainly seen many people get it wrong and therefore make it so they get an overall incorrect results when they're trying to do their analysis. Generally, in industry, what you find is people are really interested in the loop gain, and mainly for stability, as well as input impedance and output impedance changes. But they're really focused, they're also focused on the overall gain of the circuit, but they're really also focused on stability. So stability becomes an overriding factor in when you're using feedback analysis. Now the stability should not depend and does not depend on where the input is applied or where the output is taken. So if I give you a circuit and I zero my input and I don't tell you where the output is, you should be able to look at that feedback circuit and tell me how stable it is, whether it's got a good phase margin, not a good phase margin, and things like that. Turns out that in this four circuit approach for feedback is the phase margins change depending upon where you apply your input and where you may take your output. And so it results in some very strange things that go on in the phase margin. So then you have to leave the 4 feedback approach, zero your input, and just ignore that whole approach. And then you wonder why you used it at all in the first place. And in fact, people don't. Finally, the last one is this 4 feedback approach. It's difficult to account for a bidirectional behavior in the beta circuit. It can be done, but it's a challenge. And most textbooks will even ignore this because they'll say, well, it's usually not an important factor, so we just won't take that into account. Turns out it is very critical in many circuits. In switch capacitor circuits, it's critical to take this effect into account. And so it turns out that the 4 feedback approach makes it difficult to use, and yet the method we're looking at, is not difficult. So we can easily account for the bidirectional behavior of beta. Remember, if we looked at beta, here's an example here, there's a transfer function going from this point to this point, but there's also a transfer function going from this point back through this circuit. So there's a transfer function, it's just a passive network. So it has a bidirectional nature, and that's common in the beta circuit. If you look at the original circuit, we've assumed in this case that beta was unidirectional, going this direction, but in actual fact it goes in both directions. And so, as I said, it can be taken into account in the 4 feedback structure, but it's very challenging to do, and many people will do that incorrectly. And yet this other approach is done fairly straightforward. So what we find instead that we're going to be using what's called a loop gain approach. So this loop gain approach we'll be talking about in the other videos. It's very closely related to something called a return ratio approach. The return ratio approach was developed a number of years ago. It's well described in a textbook called Analysis and Design of Analog Integrated Circuits by Gray, Meyer, Hurst, and Lewis in a 2009 textbook. So why not just use the return ratio approach? Well, there's a slight difference. The method we're going to talk about will use loop gain instead of the return ratio. And the reason for that is the return ratio approach does not really allow a smaller feedback loop. It requires that there's only one feedback loop in the entire circuit. If you have multiple feedback loops in the entire circuit, then you'll get different return ratios depending upon which of the elements that you use. However, in the loop gain analysis, we won't see that. So what we allow is the loop gain approach allows smaller feedback loops to be inside a larger feedback loop. And a very common example of this is resistor degeneration. It turns out resistor degeneration in a common source amplifier is actually a feedback loop. And that resistor degeneration makes the return ratio approach do some funny results when you're looking for phase margin or other things. So in order to get around that, we just use a loop gain rather than the return ratio. As I mentioned, we'll be going over that in another video. So thanks for watching, and that ends this video.